Real search often lives in more than one backend. Federated Retrieval plus RRF lets Postgres and OpenSearch return one ranked result list. You'll learn how the pieces fit into a workflow that searches separate stores and blends their ranked documents. I'm Professor Pi, teaching Search and IR with simple Python. Many projects mix systems, relational rows in Postgres and full text in OpenSearch. Users don't want two separate tabs. They want one sensible list. Federated Search closes that gap by asking each system for candidates, then merging their strengths into a single view. The practical goal is straightforward. Keep candidate rounds fast and produce a stable ranked list that respects both relational signals and text relevance. The plan is simple and incremental. Get top candidates from each store. Turn every result into a shared shape. Finally, fuse ranks with a lightweight rule so scores from different systems don't clash. The upside is obvious. Each system keeps doing what it does best. The downside is operational complexity. You need to watch freshness and permissions more closely. We will build a small federated flow that queries Postgres and OpenSearch, normalizes results into a compact SearchHit shape, and fuses them with Reciprocal Rank Fusion. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's begin by showing how a single backend row is turned into the common document shape. This snippet normalizes one backend row into the shared SearchHit shape. Federated search gets messy when every backend returns a different object because ranking code starts depending on source-specific fields. SearchHit gives the rest of the tutorial one compact contract. Backend tells us where it came from, doc ID identifies the item, title and text carry display data, and rank preserves the original backend order. The row is tiny on purpose, but it represents the kind of document metadata you would get from Postgres. The visible output shows the normalized doc ID, which proves downstream code can stop caring about the original row format. Now we need a real Postgres query that returns rows we can normalize. This example queries Postgres with psycopg and converts database rows into SearchHit objects. In many real systems, Postgres already owns structured content, permissions, or freshness rules, so copying everything into a search index can add complexity. PG is a live psycopg connection, and PG execute runs a parameterized query using Q rather than string building user input into SQL. The order by ID keeps the small demo stable, while enumerate records the backend rank that RRF will need later. The visible output shows how many Postgres results are now available in the common shape. Postgres gives structured candidates, but OpenSearch gives ranked text matches. We must pull those two and keep their rank intact. This code queries OpenSearch with opensearch-py and maps each hit into SearchHit. OpenSearch may rank text matches differently from Postgres, especially when analyzers, BM25 fields, or index mappings are doing useful work. Search is the OpenSearch client. Body holds the match query, and search.search returns the usual hit structure from the index. The conversion keeps ID, source title, source body, and the rank from enumerate, so OpenSearch can participate without taking over the whole architecture. The visible output shows the OpenSearch side has produced its own ranked candidate list. At this point, we have two ranked lists in the same shape, but raw scores are incompatible. We need a fusion rule that trusts ranked positions instead of raw scores. This snippet applies Reciprocal Rank Fusion to the combined Postgres and OpenSearch candidate lists. Raw scores from different systems are often not comparable, so RRF uses rank positions instead of trying to normalize BM25-like scores against SQL-derived scores. The RRF function adds a small contribution for every appearance of the same doc ID, then sorts by fuse score with doc ID as a deterministic tiebreaker. Increasing K flattens the influence of top ranks, while decreasing it rewards first-place hits more aggressively. The visible output shows the winning document and its fused score, which is the core merge step. With Fusion working, we wrap the pieces into a single federated search call so callers only ask one function for results. This example wraps the Postgres, OpenSearch, and RRF pieces into one federated search function. The useful baseline is not a giant platform. It is a repeatable flow that asks each backend for candidates, converts both result formats into SearchHit, and sends one combined list into RRF. PG execute keeps Postgres in the loop for relational content, while search.search keeps OpenSearch in the loop for index text relevance. The size parameter controls how many candidates each backend contributes and how many fused IDs come back. The visible output shows the final ranked document IDs from the federated layer. This toy flow maps well to an engineering checklist. In a production service, you would respect row-level permissions from Postgres, keep OpenSearch index mappings aligned with user queries, and cache-fused results for hot queries to reduce latency. Federated search is combining candidates and fusing ranks. Use it when data lives in multiple specialized stores and moving everything into one index is costly. Remember one caveat: more systems means more operational surface, so plan checks for freshness and access control. A practical next step is tuning the RRF K parameter and the per backend candidate size. Try increasing size to 20 and lowering K to 1.5. Then measure top 5 overlap and latency on a real user query set like your product search logs. If short, practical IR helps, subscribe and watch the IR videos.